Look up at the night sky right now, find the constellation Cassiopeia, and know that at this very moment, 2.5 million years worth of light is arriving at your eyes from a galaxy that contains 1 trillion stars. A galaxy so massive that it's hurtling toward us at 250,000 miles per hour. A galaxy that will one day merge with our own Milky Way in the most spectacular cosmic dance the universe has ever choreographed. And you're here, right now, about to discover why the Andromeda Galaxy isn't just another smudge of light in the darkness, but rather the key to understanding everything about where we came from, where we're going, and what it means to be a conscious being floating on a rock in an incomprehensibly vast ocean of space and time. Imagine for a moment that you could compress the entire history of human civilization into a single second. Every empire that rose and fell, every invention, every war, every love story, every child born and every elder who closed their eyes for the last time, all of it squeezed into one heartbeat. And even then, the light that left Andromeda when our ancestors were barely human, when we were still learning to walk upright on the African savannah, when we had not yet discovered fire or language or art, that light has been traveling through the void for so long that it has crossed distances your mind literally cannot comprehend. And yet here it is, touching your retina, carrying with it secrets about the fundamental nature of reality itself. You need to understand something crucial before we go any further, something that will change how you see everything around you. The Andromeda Galaxy that exists in the sky tonight is not the Andromeda Galaxy as it exists right now. What you're seeing is a ghost, a phantom from the deep past. Because when you look at Andromeda, you're looking back in time 2.5 million years. And this isn't poetic language or metaphor. This is literal fact. The photons entering your eye left that galaxy before the genus Homo even existed, before our ancestors had developed the cognitive capacity to wonder about the lights in the sky, before we could ask the question that defines our species: what is out there, and what does it mean for us? The story of how we discovered Andromeda is itself a journey through human ambition, error, genius, and the slow, painful process of expanding our consciousness beyond the tiny bubble of our immediate experience. For thousands of years, humans looked at that fuzzy patch of light and called it a nebula, a cloud, a mist, something local, something nearby, something that belonged to our stellar neighborhood. And why wouldn't they think that? After all, we have an inherent bias toward believing that we are at the center of everything, that the universe revolves around us, that what we see is all there is to see. And this bias has been the greatest obstacle to human understanding throughout our history. But it's also been the fuel for our greatest triumphs, because every time we've been forced to confront how wrong we were, how small we actually are, how little we actually matter in the grand scheme of cosmic events, we've responded not with despair, but with wonder, not with surrender, but with an even fiercer determination to understand. In the early 1920s, there was a debate that would determine the scale of everything we thought we knew about existence. Astronomers were divided into two camps. One side believed that the entire universe consisted of just our Milky Way galaxy, and that all those fuzzy nebulae were simply clouds of gas and dust within our own stellar system. The other side proposed something so audacious that it seemed almost insane. They suggested that some of these nebulae were actually separate galaxies, island universes as they called them, each containing billions of stars, each separated from us by distances so vast that our minds would struggle to process them. And the fate of human cosmology hung in the balance. Were we living in a universe that was comprehensible, manageable, relatively small, or were we living in something so much larger, so much more magnificent and terrifying than we had ever imagined? Enter Edwin Hubble, a man whose name would become synonymous with the Hooker telescope at Mount Wilson Observatory. Hubble made a measurement that changed everything. He identified Cepheid variable stars in the Andromeda Nebula, stars whose brightness pulses in a regular pattern that allowed him to calculate their distance. And when he did the math, when he worked out how far away these stars had to be based on how dim they appeared, despite their intrinsic brightness, he realized something that must have made his hands tremble as he wrote it down. Andromeda wasn't just a nebula in our galaxy. It was a galaxy unto itself, and it was nearly 1 million light-years away, a number that has since been revised upward to 2.5 million light-years. But even that original calculation was enough to shatter every assumption humanity had held about the scale of existence. Think about what this meant for the people alive at that moment. Imagine waking up one day and discovering that your house isn't just your house, but rather one room in a building so enormous that it contains millions of other houses, each one potentially home to other families, other stories, other dramas playing out across distances that make the ocean between continents look like a puddle. That's what Hubble's discovery did to our conception of reality. It took the universe we thought we knew and multiplied it by factors that defied comprehension. And Andromeda was the key that unlocked that door. The first definitive proof that we live in a universe of galaxies, a cosmos so vast that our entire solar system is less than a speck of dust in a single room of an infinite mansion. But here's where the story gets even more fascinating, even more emotionally overwhelming. Because Andromeda isn't just sitting out there peacefully in the void, it's coming for us. And I don't mean that in some distant abstract way. I mean that right now, as you listen to these words, the Andromeda Galaxy is moving toward the Milky Way at approximately 110 kilometers per second. That's about 250,000 miles per hour. And this isn't some minor perturbation. This isn't a cosmic coincidence. This is the inevitable result of gravity. The same force that keeps your feet on the ground, that makes apples fall from trees, that force is right now pulling two massive galaxies toward each other in what will be the most spectacular collision the local universe will witness for billions of years. Now I need you to really sit with this for a moment, because the implications are staggering. In approximately 4 billion years, give or take a few hundred million, the night sky that our distant descendants see, assuming humanity or whatever we evolve into still exists, will be completely transformed. Instead of seeing Andromeda as a distant fuzzy patch, they will see it dominating the entire sky, a magnificent spiral of billions of stars stretching from horizon to horizon. And as the two galaxies interpenetrate each other, as they begin their gravitational dance, individual stars will be flung out into intergalactic space. New stars will form from colliding gas clouds. Black holes at the centers of both galaxies will spiral toward each other and eventually merge, releasing gravitational waves so powerful that they will ripple through the fabric of space-time itself, detectable by any civilization with the technology to measure such things from billions of light-years away. The beautiful thing, the thing that should fill you with a sense of cosmic serenity, even as it fills you with awe, is that despite this catastrophic collision between two galaxies, despite hundreds of billions of stars swirling and mixing and being scattered, the chances of any two individual stars actually colliding is almost zero, because space is so vast, so incomprehensibly empty, that even when galaxies collide, the stars themselves are like grains of sand in a stadium, so spread out that they can pass through each other like ghosts. And if Earth and our solar system still exist when this happens, if our planet hasn't already been consumed by the sun's expansion into a red giant, we will probably survive the merger unscathed, perhaps flung out into a different orbit, perhaps finding ourselves in a completely different part of the newly formed galaxy that astronomers have already named Milky Way, a portmanteau of Milky Way and Andromeda, a single massive elliptical galaxy that will be the legacy of this cosmic marriage. Let me take you deeper into what Andromeda actually is, not just as a collection of facts and figures, but as a real place, a physical location in the universe, where if you could somehow travel there, you would find yourself surrounded by the same kinds of wonders that exist in our own galaxy. Planets orbiting alien suns, potentially civilizations looking back at us, wondering if anyone is out there. Stellar nurseries where new stars are being born in clouds of gas and dust. Supernova remnants where dead stars have scattered the heavy elements necessary for life across vast distances. Black holes devouring matter and spitting out jets of radiation that stretch for thousands of light years. All of this is happening in Andromeda right now. Or rather, it was happening 2.5 million years ago, and by the time we see it, it's already ancient history, already done, already moved on to whatever comes next. The Andromeda Galaxy measures approximately 220,000 light-years across, making it about twice the diameter of the Milky Way, and it contains roughly 1 trillion stars compared to our galaxy's estimated 200 to 400 billion. Which means that if you wanted to count every star in Andromeda, even if you counted 1 star per second without ever stopping to eat or sleep or rest, it would take you more than 31,000 years to finish counting. And that's just the stars. We haven't even begun to talk about the planets, the moons, the asteroids, the comets, the nebulae, the star clusters, all the structures and phenomena that make up a complete galaxy. And when you start to multiply this by the estimated 2 trillion galaxies in the observable universe, your mind begins to approach the limits of what it can process. You start to feel that existential vertigo that comes from truly understanding how cosmically insignificant we are, and yet how miraculous it is that we exist at all, that we're able to contemplate these things, that the universe has become conscious of itself through us. I want to tell you about the satellite galaxies of Andromeda because they reveal something profound about how structure forms in the universe. Andromeda doesn't travel alone through the cosmos. It's accompanied by at least 14 known dwarf galaxies that orbit around it like moons around a planet. The 2 largest of these are Messier 32 and Messier 110, both of which are elliptical galaxies that contain millions of stars. And these satellites are slowly being torn apart by Andromeda's immense gravity, their stars being stripped away and absorbed into the larger galaxy in a process that happens so slowly it's invisible to human timescales, but so inevitably that it's like watching a river slowly erode a mountain. Given enough time, these dwarf galaxies will cease to exist as distinct objects and will become part of Andromeda itself, their stars scattered throughout the larger system. Now, their identity lost, but their matter preserved, transformed, incorporated into something larger than themselves. This process of galactic cannibalism isn't unique to Andromeda. Our own Milky Way has done the same thing, consuming dozens of smaller galaxies over its lifetime, and there's evidence that we're currently in the process of absorbing the Sagittarius Dwarf Elliptical Galaxy, a small galaxy that's been stretched into a stream of stars wrapped around our galaxy like ribbon around a package. And this tells us something important about how galaxies grow and evolve. They're not static objects that formed in the early universe and remained unchanged. They're dynamic systems that grow through accretion and merger, through violence and collision, through the slow, steady accumulation of mass over billions of years. And understanding this process helps us understand our own origins, because the Milky Way, as it exists today, is the product of countless mergers and acquisitions. Every atom in your body was forged in stars that may have originally belonged to entirely different galaxies before they were incorporated into our own. You are literally made of the remnants of ancient cosmic collisions. And that should make you feel connected to this story in the most intimate way possible. The central region of Andromeda harbors one of the most fascinating and terrifying objects in the known universe, a supermassive black hole with a mass estimated at somewhere between 100 and 230 million times the mass of our Sun. This is the gravitational anchor around which the entire galaxy rotates, and studying it has revealed something unexpected, something that challenges our understanding of how black holes form and grow, because at the very center of Andromeda's nucleus there appears to be not just one supermassive black hole, but possibly 2, the result of a previous galactic merger that hasn't yet reached its final conclusion. The 2 black holes are spiraling around each other, slowly drawing closer together. And eventually they will merge in an event that will release more energy in a fraction of a second than our Sun will produce in its entire 10 billion year lifetime. And when I say energy, I mean that the merger will produce gravitational waves so powerful that they will cause every atom in your body to oscillate in a tiny dance as the waves pass through Earth, connecting you directly to an event happening 2.5 million light-years away, making you a participant in cosmic history, whether you realize it or not. Let's talk about the spiral structure of Andromeda, because it's one of the most beautiful and mysterious aspects of galaxies in general. Those elegant sweeping arms that curve outward from the galactic center aren't just random patterns. They're density waves, regions where stars and gas clouds pile up like cars in traffic. And as material moves through these density waves, it gets compressed, and that compression triggers star formation, which is why the spiral arms appear bright. They're filled with young hot blue stars that live fast and die young, burning through their nuclear fuel in just a few million years before exploding as supernovae. And those supernovae trigger more star formation in a cascade effect that keeps the spiral arms lit up like a string of lights on a cosmic Christmas tree. But here's the thing. The actual stars don't stay in the spiral arms. They move through them. The arms themselves are like waves on the ocean. They persist even as the individual water molecules move in and out of them. And understanding this took decades of research and argument and careful observation. And it's still not completely clear what maintains these structures over billions of years, what prevents them from winding up and disappearing. This is one of the great unsolved problems in astrophysics, and Andromeda, being close enough to study in detail, is one of our best laboratories for trying to figure it out. I need to tell you about something that's going to sound impossible, but is absolutely true. When you look at Andromeda with your naked eye, the photons that hit your retina have been traveling for 2.5 million years. They've crossed a void so vast that if you could somehow mark the path they took with a line, that line would cross regions of space where the density of matter is so low that there might be only a handful of atoms per cubic meter. Regions emptier than any vacuum we can create on Earth, emptier than the space inside an atom. And yet these photons traveled in perfectly straight lines, never deviating, never stopping, moving at the speed of light, which is not just fast, but rather the absolute cosmic speed limit, the speed at which causality itself propagates, the speed at which information can travel from one point in the universe to another. And the fact that these photons maintained their coherence, maintained their information about where they came from and what they carried for that entire journey, and then happened to intersect with your eye at exactly this moment in history, that's not just remarkable. No, it's a miracle of mathematics and physics playing out on the grandest scale imaginable. Now I want you to think about the civilizations that might exist in Andromeda right now. Not as they were 2.5 million years ago, but as they exist in their present moment, which we cannot see and will not see for another 2.5 million years. If intelligent life exists there, if there are beings looking out at the cosmos trying to understand their place in it, just as we are identical. They are looking at our galaxy as it existed 2.5 million years ago. They're seeing the Milky Way before modern humans existed, before our species emerged, before we developed language or art or science. And if they're sending signals toward us, if they're trying to communicate, those signals are still in transit, and we won't receive them for millions of years. And if we send signals to them, they won't receive those signals until our civilization is either transcended into something unrecognizable or collapsed back into dust. This is the tyranny of distance in the universe. This is why the Fermi paradox exists. Why we haven't detected alien civilizations despite the billions of potentially habitable planets that must exist. Because space is so vast and time is so long. And the window during which two civilizations might exist simultaneously and be capable of communication and be close enough to actually exchange messages is so vanishingly small that the silence we hear when we listen to the cosmos might not mean we're alone, but simply that we're early or late, or just too far apart to ever say hello. The chemistry of Andromeda is different from our galaxy in subtle but important ways. Spectroscopic analysis of the stars in Andromeda reveals that the galaxy as a whole has a slightly different metallicity than the Milky Way, meaning the abundance of elements heavier than hydrogen and helium is different. And this tells us something about the history of star formation in that galaxy, about how many generations of stars have lived and died and seeded the interstellar medium with the products of their fusion, carbon and nitrogen and oxygen, and all the other elements that make life possible. And the fact that we can measure these differences across millions of light years using nothing more than the light from those stars broken apart into its component colors is itself a testament to human ingenuity, to our ability to extract information from the universe using nothing but careful observation and mathematical reasoning. And it should make you appreciate that every time you look at the periodic table of elements, you're looking at the ashes of dead stars. You're looking at the product of cosmic alchemy that takes place in the hearts of suns and in the explosive deaths of supernovae. And every atom of oxygen you breathe was created in a star that exploded before our solar system even existed. And some of those atoms might have originally come from a star in what is now the Andromeda Galaxy, ejected into intergalactic space billions of years ago and eventually incorporated into the cloud of gas and dust that... Tragedy is that even though we might both exist, even though we might both be asking the same questions at the same time, the distances are so vast that we can never meet, never communicate, never share our stories or our science or our art, then unless we develop technologies that we cannot currently imagine, ways of circumventing the speed of light limitation, wormholes or warp drives, or quantum entanglement communication systems that exist only in theoretical physics papers and science fiction. But the fact that we can imagine these things, the fact that we can write equations that describe them even if we don't know how to build them, that tells us something important about human nature. We are not content with limitations. We push against boundaries. We refuse to accept that anything is truly impossible. The star formation rate in Andromeda has slowed compared to what it was billions of years ago. The galaxy is middle-aged now. Most of its gas has already been converted into stars, and while new stars are still being born in the spiral arms and in regions of particular density, the glory days of rapid star formation are behind it. Andromeda is settling into a more sedate existence, at least until the collision with the Milky Way reignites the star formation process by compressing gas clouds and triggering a new burst of stellar birth. And this life cycle of galaxies, this pattern of birth and growth and maturity and eventual merger, it mirrors in some ways the life cycle of living things. And it makes you wonder if there's something fundamental about the universe that favors these patterns, these cycles of creation and destruction and transformation. Whether we're talking about stars or galaxies or biological organisms or even ideas and civilizations, everything seems to follow a similar arc. And maybe that's not a coincidence. Maybe there are deep mathematical principles underlying all of reality that manifest at every scale, from the quantum to the cosmic, patterns within patterns within patterns, fractals of existence repeating from the infinitesimal to the infinite. The brightest globular cluster in Andromeda is called Mile 2, or G1, and it contains hundreds of thousands of stars packed into a region only about 200 light-years across. These are old stars, ancient stars that formed when the universe was young, and they orbit the galactic center in elliptical paths that take them swooping through the disk and back out into the halo. And studying these globular clusters helps us understand how galaxies form, because the clusters are like fossils. They preserve information about the conditions that existed billions of years ago. And by measuring their chemical composition and their distribution and their orbital characteristics, we can reconstruct the history of the galaxy. We can tell which parts formed first, which parts were accreted later through mergers, which regions have been enriched by multiple generations of supernovae. It's like being a detective examining clues to solve a mystery, except the mystery is the origin and evolution of an entire galaxy, and the clues are written in light and motion and mathematical relationships. And the fact that we can solve this mystery at all, that we can look at Andromeda from 2.5 million light-years away and tell the story of its life, that's perhaps the greatest achievement of human science. Our ability to take limited information and through careful reasoning and mathematical modeling extract truth from the cosmos. I want to talk about the dark matter halo that surrounds Andromeda, because it's one of the most profound mysteries in modern physics. When we measure the rotation speed of stars and gas in the outer regions of Andromeda, we find that they're moving faster than they should be based on the visible mass of the galaxy. The stars should be flying off into intergalactic space, but they're not. They're held in orbit by gravity, but not the gravity from the stars and gas and dust that we can see. There has to be additional mass, a lot of additional mass, and we call it dark matter, even though we don't know what it is. It doesn't emit light, it doesn't absorb light, it doesn't interact with electromagnetic radiation at all as far as we can tell. We can only detect it through its gravitational effects. And the best estimates suggest that Andromeda contains about 5 to 10 times more dark matter than regular matter, which means that the galaxy we see, that beautiful spiral of stars, is just the tip of the iceberg, the visible part of a much larger structure. And this dark matter halo extends far beyond the visible edge of the galaxy, perhaps stretching halfway to the Milky Way. And our own dark matter halo probably extends halfway to Andromeda, which means they might already be touching. These two invisible oceans of mysterious matter, already interpenetrating, already beginning their long, slow gravitational embrace. The speed at which Andromeda is approaching us tells us something important about the large-scale structure of the universe. Most galaxies are moving away from us because the universe is expanding. Space itself is stretching, carrying galaxies apart like raisins in rising bread dough. But Andromeda is close enough that the mutual gravitational attraction between it and the Milky Way overcomes this expansion. We're bound to each other. We're part of the same local group of galaxies, and this local group is itself part of a larger structure called the Laniakea supercluster, a collection of about 100,000 galaxies spread across 520 million light-years, all moving together through space like a flock of birds flying in formation. And Laniakea itself is being pulled toward an even larger concentration of mass called the Shapley supercluster. And all of this is happening in the context of an expanding universe that over billions of years will eventually cause all structures beyond our local group to disappear beyond our cosmic horizon, to redshift into invisibility as space expands faster than light can traverse it, which means that the universe our distant descendants will observe will be much smaller than the universe we see today. They will live in an island of light, surrounded by darkness. And if they're not careful, if they don't preserve our records and our observations, they might conclude that the universe consists of just a single group of galaxies, and that beyond that, there is nothing. They might make the same mistake our ancestors made when they thought the Milky Way was all there was. And this raises a terrifying question. How do we know we're not making a similar mistake right now? How do we know that what we call the observable universe isn't just a tiny fraction of what actually exists? How many truths about reality are hidden from us, not because they're mysterious or complex, but simply because they're too far away or too faint or too different from what we expect to detect with our current instruments and theories? There's something called the Andromeda paradox that I need to tell you about, because it reveals the bizarre nature of relativity and simultaneity. Imagine there's a person on Earth looking at Andromeda, and there's an alien in Andromeda looking back at Earth. According to special relativity, what events they consider to be happening now depends on their state of motion. If the alien is moving toward Earth, then from their perspective, what's happening now on Earth might be something that, from our perspective, won't happen for thousands of years in the future. And if they're moving away from Earth, then from their perspective, what's happening now on Earth might be something that, from our perspective, happened thousands of years in the past. This seems to create a paradox because it suggests that the future already exists. That time is not flowing, but rather everything that will ever happen has already happened from certain perspectives. And this has profound implications for free will and determinism and the nature of time itself. And the fact that you can derive this conclusion from the simple postulate that the speed of light is the same for all observers should tell you something about how weird the universe actually is. How the common sense intuitions we develop, living in our low-velocity, low-gravity environment, completely fail when we extend them to cosmic scales and relativistic speeds. The gas clouds in Andromeda are being mapped in incredible detail using radio telescopes that can detect the emission from neutral hydrogen. And these maps reveal structure within structure, filaments and bubbles and shells created by stellar winds and supernova explosions. And by studying how this gas moves, how it flows from one region to another, we can see the galaxy breathing. We can watch material cycle from the interstellar medium into stars, and then back into the interstellar medium in an endless recycling process. And this cycle is what maintains star formation over billions of years. Without it, all the gas would be locked up in stars or remnants, and the galaxy would go dark. But instead, we see this beautiful cosmic ecology where death feeds life, where supernovae create the heavy elements and shock waves that trigger the next generation of stars, where stellar winds blow bubbles in the gas that compress and fragment and collapse into new stellar nurseries. And all of this is governed by physics, by equations we can write down and simulate on computers, and yet the complexity that emerges from these relatively simple rules is staggering, is beautiful in a way that transcends mere aesthetics and touches something deeper, some fundamental truth about how complexity and structure emerge from simplicity and chaos. Let me tell you about the transient events we've observed in Andromeda, the supernovae that blaze briefly and then fade, each one representing the death of a star, each one releasing as much energy in a few weeks as our sun will emit over its entire lifetime. We've catalogued dozens of these explosions in Andromeda over the decades, and each one tells us something about the types of stars that exist in that galaxy, about the physics of stellar evolution and death. And here's something that should give you pause. Every supernova we observe in Andromeda actually happened 2.5 million years ago. That star died before humans existed, and the light from its death has been traveling through space all this time. And it just happened to arrive at Earth during the tiny sliver of cosmic history when we have telescopes pointed in that direction, when we have the knowledge and technology to understand what we're seeing. And this means that most of the supernovae that have occurred in Andromeda over its history went completely unobserved. Their light passed through the solar system before there was anyone here to see it, or it hasn't arrived yet and won't for millions of years after our species has either evolved into something else or gone extinct. And this should make you appreciate how precious and fleeting this moment is. This brief window during which we can observe and understand and record the universe. We are the universe's way of knowing itself, and that makes every observation, every measurement, every insight we gain a victory against the cosmic indifference that surrounds us. The magnetic field of Andromeda has been partially mapped, and it shows a large-scale structure that follows the spiral arms. The magnetic field is generated by the motion of charged particles in the interstellar medium, and it plays a role in star formation by providing support against gravitational collapse in some regions and channeling material in others. And the fact that galaxies have magnetic fields at all is somewhat mysterious. We understand the basic mechanisms of how they're generated, but the details of how they achieve such large-scale coherence, how they maintain their strength over billions of years, these questions are still being actively researched. And Andromeda serves as a crucial test case, because it's close enough that we can map its magnetic field in detail, but distant enough that we see the entire structure at once, rather than being embedded in it like we are with the Milky Way. And this combination of proximity and perspective makes it invaluable for testing our theories of galactic magnetism and cosmic ray propagation and all the other phenomena that depend on electromagnetic fields in space. I need to address something that often gets overlooked in discussions of cosmic events. The emotional weight of knowing that Andromeda is approaching, that a collision is inevitable, that the night sky will change, that our galaxy as we know it will cease to exist. There's something almost melancholy about this knowledge, like watching a beautiful sunset and knowing that night is coming. And yet there's also something redemptive about it, because the merger won't destroy Andromeda or the Milky Way, it will transform them. It will create something new, something that has never existed before, a galaxy that will be the product of billions of years of separate evolution coming together. And if you think about it, this is happening at every scale in the universe, particles colliding and combining to form atoms, atoms combining to form molecules, molecules combining to form cells, cells combining to form organisms, organisms combining to form societies, stars combining their light to form galaxies, galaxies combining to form clusters. And at each level of organization, something new emerges, properties and behaviors that couldn't be predicted from the components alone. And this is the fundamental creativity of the universe, its tendency to build complexity, to create structure, to make possible things that weren't possible before. And we are part of that process. We are one of the ways the universe becomes more complex, more aware, more capable of acting with intention, rather than just following deterministic physical laws. The stellar populations in Andromeda can be divided roughly into three components: the thin disk containing young stars and ongoing star formation, the thick disk containing older stars, and the halo containing the oldest stars and globular clusters. And by studying the properties of these different populations, their ages and chemical compositions and kinematics, we can reconstruct the assembly history of the galaxy. We can tell that the halo formed first through the coalescence of smaller proto-galactic fragments, that the disk formed later through the accretion of gas that settled into a rotating plane, that the spiral structure developed through gravitational instabilities in this disk. And we can identify stars that were born in smaller galaxies that were later accreted by Andromeda, immigrants from other stellar systems that now orbit in the halo as evidence of ancient cosmic violence. And in a very real sense, we're looking at galactic archaeology. We're excavating the past using light as our shovel and mathematics as our interpretation framework. And the fact that we can do this at all is a testament to the power of the scientific method, to our ability to develop theories that make testable predictions and then go out and test them. And when the predictions fail, to revise our theories and test again. This iterative process of hypothesis and observation and revision is how we've gone from thinking the universe was a few thousand years old and a few thousand miles across to knowing that it's 13.8 billion years old and contains trillions of galaxies spread across billions of light years. And that journey from ignorance to knowledge, from mythology to science, that's one of the great achievements of our species, right up there with art and music and literature, as things that make human existence meaningful. There are novae as well as supernovae in Andromeda, smaller explosions that occur when a white dwarf star accretes material from a companion and undergoes a thermonuclear explosion on its surface. And monitoring these novae helps us understand binary star evolution, the complex dance of two stars orbiting each other, exchanging mass, influencing each other's evolution. And some fraction of the stars in Andromeda are in binary systems, possibly more than half, which means that the solitary sun we orbit is actually unusual. Most stars have companions. Most stellar evolution happens in the context of gravitational relationships with other stars. And this changes everything about how we think about planetary systems and habitability, because planets in binary star systems might have unstable orbits or might be subjected to varying amounts of radiation as their stars orbit each other. Or they might be in particularly favorable configurations where the combined output of both stars extends the habitable zone. And we don't know how common life is in the universe. We don't know if it arises inevitably wherever conditions are suitable, or if it requires some special spark, some unlikely coincidence of chemistry and energy and time. But we do know that the number of potential habitats is enormous. Every star is potentially a sun for planets. Every planet is potentially a world where chemistry could become biology, where molecules could organize themselves into patterns that persist and replicate and evolve. And when you multiply the number of stars in Andromeda by the number of planets per star, by the fraction that might be habitable, you get numbers so large that the absence of detectable alien civilizations becomes the puzzle rather than their existence. And this is the Fermi paradox again. Where are they? Why haven't we heard from them? And one got it. Below is your exact text, with only punctuation and spacing corrected. No words added. No words removed, same ending, comma kept. Of ancient cosmic violence. And in a very real sense, we're looking at galactic archaeology. We're excavating the past using light as our shovel and mathematics as our interpretation framework. And the fact that we can do this at all is a testament to the power of the scientific method, to our ability to develop theories that make testable predictions and then go out and test them, and when the predictions fail, to revise our theories and test again. This iterative process of hypothesis and observation and revision is how we've gone from thinking the universe was a few thousand years old and a few thousand miles across to knowing that it's 13.8 billion years old and contains trillions of galaxies spread across billions of light years. And that journey from ignorance to knowledge, from mythology to science, that's one of the great achievements of our species, right up there with art and music and literature, as things that make human existence meaningful. There are novae as well as supernovae in Andromeda, smaller explosions that occur when a white dwarf star accretes material from a companion and undergoes a thermonuclear explosion on its surface. And monitoring these novae helps us understand binary star evolution, the complex dance of two stars orbiting each other, exchanging mass, influencing each other's evolution. And some fraction of the stars in Andromeda are in binary systems, possibly more than half, which means that the solitary sun we orbit is actually unusual. Most stars have companions. Most stellar evolution happens in the context of gravitational relationships with other stars. And this changes everything about how we think about planetary systems and habitability, because planets in binary star systems might have unstable orbits or might be subjected to varying amounts of radiation as their stars orbit each other. Or they might be in particularly favorable configurations where the combined output of both stars extends the habitable zone. And we don't know how common life is in the universe. We don't know if it arises inevitably wherever conditions are suitable, or if it requires some special spark, some unlikely coincidence of chemistry and energy and time. But we do know that the number of potential habitats is enormous. Every star is potentially a sun for planets. Every planet is potentially a world where chemistry could become biology, where molecules could organize themselves into patterns that persist and replicate and evolve. And when you multiply the number of stars in Andromeda by the number of planets per star, by the fraction that might be habitable, you get numbers so large that the absence of detectable alien civilizations becomes the puzzle rather than their existence. And this is the Fermi paradox again. Where are they? Why haven't we heard from them? And one possible answer is that we're looking at the wrong timescale, that civilizations rise and fall on timescales of thousands or tens of thousands of years, while galaxies exist for billions, so the chance of two civilizations existing simultaneously and being able to communicate is vanishingly small. Or perhaps intelligence is common, but technological civilization is rare because most species destroy themselves before they reach the stars. Or perhaps intelligence is rare and we're alone in our corner of the universe, orphans in the cosmos with no one to talk to except ourselves. And I don't know which possibility is more terrifying, that we're alone or that we're not, that we're unique or that we're common, that the universe is silent because there's no one else out there, or because everyone else has already learned that silence is the safest strategy in a dark forest where predators might be listening. The kinematics of Andromeda reveal something fascinating. The galaxy is not just moving toward us, but also rotating, spinning around its axis once every few 100 million years. And by measuring the Doppler shift of stars on opposite sides of the galaxy, we can map this rotation. We can see that one side is moving toward us slightly faster than the other, because it's rotating in our direction, while the other side is rotating away. And this rotation is what prevents the galaxy from collapsing under its own gravity, the same way Earth's motion around the sun prevents it from falling into the sun. Everything in the universe is either falling or orbiting. There is no such thing as standing still. Everything is in motion relative to everything else. And this motion is governed by the interplay of gravity and inertia, the tendency of masses to attract each other, and the tendency of moving objects to continue moving in straight lines. And from these two simple principles, from F equals ma and the inverse square law of gravity, we can derive the entire structure of the cosmos, the orbits of planets, the trajectories of spacecraft, the evolution of galaxies, the expansion of the universe itself. And this is the power of physics, that a few fundamental laws operating over vast stretches of time can produce all the complexity and beauty we see around us. Let me tell you about the colors of Andromeda. When you look at it through a telescope with a camera that can capture long exposures, you see that different parts of the galaxy glow with different colors. The spiral arms are blue because they contain young hot stars that burn with fierce intensity. The central bulge is yellow and red because it contains older, cooler stars that have settled into a more sedate existence. And this color variation tells the story of stellar evolution. Blue giant stars live fast and die young. They burn through their hydrogen fuel in just a few million years and then explode or collapse. While red dwarf stars can persist for trillions of years longer than the current age of the universe, so long that no red dwarf that has ever formed has yet died of old age. They're all still out there, still burning, still waiting for the day billions or trillions of years in the future when their fuel runs out and they fade into darkness. And this raises an interesting question about the far future of the universe. Eventually, all the gas will be locked up in stars or stellar remnants or black holes. Star formation will cease. The last stars will die. The galaxies will go dark. And the universe will enter what's called the degenerate era, when the only sources of light are the slowly cooling white dwarfs and the occasional flash when a brown dwarf or planet falls into a black hole. And after that comes the black hole era, when even those objects have decayed, and the universe consists of nothing but black holes slowly evaporating through Hawking radiation. And after that, the dark era, when even the black holes are gone, and the universe is filled with nothing but thin soup of photons and fundamental particles spreading ever farther apart as space continues to expand. And this heat death of the universe, this eventual end state of maximum entropy, is the ultimate fate of everything, if our current understanding of physics is correct. But that's trillions upon trillions of years in the future, and who knows what might happen in that time. To action. If you enjoyed this journey through the universe, don't forget to subscribe to the channel. New videos like this are coming your way, exploring space, science, and the mysteries of the cosmos. Hit the subscribe button and stay curious.